So today we're going to be walking through the new June 2019 Further Stats 1 exam paper. So this is for the full A-level, not the AS paper, but I will be doing the AS paper eventually, so be sure to check that out when that's done. So we're looking here at question 1. There's 7 questions in total for this paper. Overall, it wasn't too bad of a paper. Question 1's a very nice introduction though, so let's have a look at question 1. So, question 1, part A. We've got a question here where it's talking about basically chocolate, so if you're hungry, not the best question to start with. It tells us that the tokens are placed in 2% of the bars it produces, so that each bar contains at most 1 token. And anyone who collects 3 of these can claim a prize. So we're told that Andrea buys a box of 40 bars of these chocolates. What's the probability that she can claim a prize? So let's write the model down first. So X is distributed. Now, how do we know what distribution this is? Well, the big giveaway here is that it's in percentages, right? In percentages. So, because it's in percentages, it's going to be binomial. We've got a fixed number of trials here. It's going to be 40 bars. So my N is 40, and my P is 2% or 0.02. Okay, so that's our model. We need to find the probability that she can claim a prize. So for Andrea to be able to claim a prize, she needs 3 of these tokens. So if I just get rid of that here, that is 3 of these tokens. So she's going to need probability of X, because that's our model. She needs at least 3, so that's going to be greater than or equal to 3, which if you write this down, this is 1 minus probability of X being less than or equal to 2. Okay, just using our knowledge of the distribution. So plugging this on your calculator now, your graphical calculator, or just using the tables, whichever you prefer, what you're going to get here is 0.04567, which the 3 significant figures will be 0.0457. Okay, so it's 3 significant figures there. There we go. I don't know why I did that equals there, so just ignore that. But yeah, 3 significant figures there. So that's part A done. That's the first 2 marks. Let's have a look at part B. It tells us Barney intends to buy bars of the chocolate 1 at a time until he can claim a prize. And it says find the probability that Barney can claim a prize when he buys his 40th bar of chocolate. So this here is binomial, but it's the negative binomial. And the reason why is because it keeps going until he gets it on the 40th bar of chocolate. So it's basically we're getting a lot of failures until we get it on the 40th bar, okay? So we need negative binomial. So negative binomial. Now this is in your formula, but you don't have to worry about memorizing this, guys. So it's going to be probably X being equal to X. So this is equal to P of X, so I'm just literally writing this down from the formula book. So it's going to be X minus 1 over R minus 1 times P to the R times 1 minus P to the X minus R. Okay, so all we need to do now is plug in our values. For our question, our X, that's our total sample here. That's what we're going to finish on. That's going to be 40. And our R, how many do we need? That's going to be 3. Okay, because he needs 3 tokens. So plugging this in now, what's this going to give us? Well, it's going to give us 39. Choose 2 because it's X minus 1. So 40 minus 1, 39. R minus 1, 3 minus 1 is 2. P to the R, so that's going to be 0.02 because our P is 0.02. So times 0.02 to the power of R, where R is 3, times 1 minus P, so that's going to be 1 minus 0.02, so 0.98 to the power of X minus R, so that's going to be to the power of 37. Plug all this on your calculator now. I'm just going to write down to 3 significant figures again. It's going to be 0.00281. 3 significant figures. And there we have it, that's part B done. And part C, I will have enough room, it's a nice easy 1 marker here. The expected number of bars, so we're still working here in the negative binomial. Now your expected number, this is going to be equal to the mean, and this is in your formula book, so you don't even have to memorize this. So mu, that's going to be equal to R over P. Okay, so nice and easy here. R is 3, P 0.02, so it's going to be 3 over 0.02. Plug that in on your calculator, what do we get? We get 150 bars. And there we have it, that's question 1, nice and easy, fully complete. Moving on to question 2 now, we have a question here dealing with the Poisson distribution. And how do we know it's the Poisson distribution? Well, looking at our question here, we're told that in a certain period time here, so 4 hours, that there's a certain amount of calls, and then the next part is asking in another time frame how many more calls might arrive. So whenever you see the data that you're looking at in terms of a certain time frame, it's going to be Poisson. Okay, so we're looking at a Poisson here. So Poisson. So for part A, it just says using a suitable model, find the probability of more than 4 calls arriving in a particular 20-minute period one morning. So we're told in a 4-hour shift, there's on average 80 calls. So this is just a reception, and then there's calls coming through. So in 4 hours, 80 calls. Okay. Well, we need to know for a 20-minute period. So we've got to adjust this now. Okay. So for 20 minutes. How many calls will there be? Well, you can divide this by 4, so that'd be 20, and then divide it by 3 to get your 20 minutes. So 8 divided by 4, that'd be 20, and divide that by 3, so that'll be 20 over 3 calls. Okay, so we can model this as a Poisson distribution, so we say X modeled by PO, and here our lambda value is going to be this 20 here. This for the 20 minutes, it'll be 20 over 3. Okay, now we just need to work out the probability that X is greater than 4, so more than 4 calls arriving. So probability X is greater than 4. So that's the same as 1 minus the probability that X is less than or equal to 4. Okay. So again, up to here now, you can use your tables, or you can just put it on your calculator. You won't penalise you for just using the calculator at this point once you've shown all the previous working. So at this point here now, to 3 significant figures, this is 0.794. And there we have it. That's the first 3 marks. Quite a nice introduction there, part A. But part B and C get a bit trickier. I've got a bit more going on. So it tells us that she's allowed 20 minutes of break time during each 4-hour shift, which she can take in 5-minute periods. So what it's asking is that if she takes a break time in 4 periods of 5 minutes each, can we work out the probability that in exactly 3 of these periods there were no calls? So how do we do this? Well, let's just work out one individual break first. So one break. Okay, so that's 5 minutes. So 5 mins. Well, we knew that for 20 mins, it was 20 over 3. So 5 mins. That's going to be this divided by 4. So times it by 1 over 4, so you're going to get 20 over 12. Which will simplify to 5 over 3. So 5 over 3. Okay. So we've got our new PO value here, our lambda. What I've got to do now is work out the probability that X is equal to 0 for one of these. So probability that X is equal to 0 using lambda is equal to 5 over 3. So if you do this on your calculator, what you'll get is 0.1889, right? So we've got that 1 there. So this is my probability of there being no calls in one shift. Now, we've got this, we've got a fixed number of trials, there's 4 periods. So now we can use a binomial distribution, okay? So if I say that Y is modeled by a binomial distribution, where my N, so there's 4 breaks, so that'll be 4. And the probability is this here. That's the probability that there's no call. So 0.1889. Okay. And we want to know that the probability in exactly 3 of these periods. So I'm working out the probability that X is equal to 3. Okay. So the probability that X is equal to 3, plugging this in your calculator again, you'll get 0.0219. Just the 3 significant figures. And there we have it. That's part B. So I'll just quickly clear all this. Now for part C, it says on another occasion, she takes 1 break of 5 minutes and 1 break of 15 minutes. So find the probability that she missed exactly 1 call in each of these 2 breaks. So we're going to model this with 2 different situations here now. So I'm going to have the situation where X is distributed with a Poisson distribution, and it's going to be 5 over 3 for 5 minutes. So 5 minutes, like we already said, that's lambda equals 5 over 3. So how do we get 15 minutes? Well, I can just times this by 3, right? So 15 minutes times this by 3. So therefore, lambda is going to be equal to 5 over 3 times 3. So that's going to be 15 over 3. Okay, so we've got 15 over 3 there. Let's work out each individual one now. So we're going to have x is lambda with 5 over 3, and then we're going to do another one again. Again, I'll call this one just x. Being a bit lazy, but call that one 15 over 3. Okay. So what we've got to work out now is the probability that x is equal to 1 for both of these, and then just times our answer, and we've simply got it. So the probability that x is equal to 1, because it's exactly 1 call. So probability that x is equal to 1 for both of them. Okay, so if I do this one first, using lambda is equal to 5 over 3, this will be 0.31479267. Okay, so I'm going to keep all my accuracy just because I don't want to lose any degrees of accuracy in my final calculation. And for this one here, this will be 0.033, I'm losing my voice, 0.03368973. So therefore, my final answer, probably that x is equal to 1. It's going to be this times by this. So it's going to be 0.314799267 times, so I'm going to write all this out just to show clearly, 3368973. Performing this calculation now, you're just going to get 0.0106. And there we have it, that's question 2 fully complete. Moving on to question 3 now, we have a question here dealing with discrete random variables. So what we've got here is we've got a bias spinner which can land the numbers 1 through to 5, and we've got these following probabilities. So it tells us it's spun 80 times and the mean of the numbers it lands on will be calculated. We've got to find an estimate of the probability that its mean will be greater than 3.25. So we've got to find probability that x is greater than 3.25. But how do we do this? Well, the first thing we could do is we could work out the expected value here. Okay, so e of x, well, how do we work out e of x for discrete random variables? Well, e of x, that's going to be the sum of these multiplied together, okay? So 1 times 0.3 plus 2 times 0.1 plus 3 times 0.2 and so on, okay? So it's going to be the summation of these. So if we do that, we do it in a bracket, it's going to be 1 times 0.3, so I'll just write 0.3 plus 2 times 0.1 plus 3 times 0.2 4 times 0.1 and finally 5 times 0.3. Okay, now if you simplify all this, work out this calculation, what you'll get is that e of x, which is equal to the mean, is equal to 3. Okay, so we get straight away that the mean is equal to 3. Now let's work out the variance, because if we can work out a value for the mean, we can work out a value for the variance of this distribution here. Well, we might be able to use some statistical information that we already know, maybe the central limit theorem, to get a distribution that we can then use. So let's work out the variance here. So e of x squared. Well, how do we do this? Very similar. What you've got here is the number on the spinner, so we're going to square this value and then times it by its corresponding probability. So this will be 1 squared times 0.3, so 0.3 plus 2 squared times 0.1 and so on, okay? So I'll write them all out. 3 squared times 0.2 plus 4 squared times 0.1 plus 5 squared times 0.3. Okay, evaluate this. What will this give us? This will give us 11.6. But okay, but this isn't my variance. We need to do another calculation, and to work that out, the way to work that out is to do this e of x squared value here, so 11.6 minus my mu squared. Okay, so minus 3 squared. So 11.6 minus 9, we're just going to get 2.6. Okay, so that's e of x squared. So now we've got a mean, we've got a variance, we can use the central limit theorem now, and we can obtain a distribution. Okay, and we know we can use the central limit theorem because we've got a large n value here, over 50. You know, we've got a pretty large n of 80 here. So using the central limit theorem now, How can we do this? Well, we can say x bar is distributed normally. Okay, remember it's going to be mu, and then my value here will be variance divided by n. Okay, so doing this now, what's this going to be? Well, we've worked out the mean, that was 3. My variance was 2.6, this will be 2.6 divided by n, which is 80. So we've got this now. Now we can actually do this. So this here, it's going to be the same, but with x bar. So x bar greater than 3.25. So now, just use your tables or your graphical calculator. Quite straightforward, just plug this into your graphical calculator, and what you'll obtain is that this is equal to 0.0828. And there we have it. We've worked out the probability that this mean will be greater than 3.25. And that's question 3 fully complete. Moving on to question 4 now, we have a very long question here, and it's split up into a few different parts, but the main core of this question is looking at the chi-squared test. So, let's just have a look at what we've got going on. So we've got this distribution here of oak trees in some woodland, and they're dividing the woodland into 80 equal squares and recording the number of oak trees in each square. So the results are summarised here in table 1, and for part A, it's asking what model should Liam use to describe the number of oak trees per square. Well, the key for this part of the question is to use this bit of information here, where it says Liam believes that the oak trees were deliberately planted with 6 oak trees per square, and that a constant proportion p, so this is the important bit, the constant proportion p survived. So, what this is saying now is that it wants us to write down how this is distributed. So, question 4a, what is the distribution here? Well, if I put t for the trees, well, the key here is where it says constant proportion. Remember, when we're looking at distributions, if you ever see the fact that it's in proportion, it's a good chance, or it's more than likely always going to be binomial. Okay, so we know this is going to be a binomial distribution. Okay, so t is distributed binomially. My n, well, how many oak trees? 6 oak trees per square. That's my fixed trial here, my fixed number, so that must be my n. And my p, well, we don't know what p is, so we're just going to write p like that, right? We don't know what p is. We can later work this out, but for now we don't know what it is, so we'll just put p. Okay, and that's simply all you've got to do for the first 2 marks. It's just understanding that it needs a binomial because we're talking about proportion. Okay, so that's part A done. Part B is 7 marks, quite a bit of work to this one. So let's have a go at it. So my mouse has decided to stop working. Okay, let's have a look at it. So part B. So this is kind of a bit of an unusual format because there's literally no room for me to write down here. I'm doing it down the sides today for this one. So hopefully you can follow along. I put it in yellow just so it makes it a bit easier to see. So let's have a go at part B. So we're given some expected frequencies in this table here, table 2. And part B just asks us to complete the test here for a chi-squared test. So let's have a look at what we've got to do first for this. Well, because it's a test, let's write down a H0 and a H1. So H0. Well, my H0 here is we're testing whether this model is going to be suitable. Okay, so if we're testing whether the model is suitable, H0 will mean that it is a suitable model. So t distributed binomially with those parameters is suitable. Okay, and a H1 will just simply be t distributed binomially, again with the same parameters, is not suitable. Okay, so that is not suitable. There we go, so just about enough room. So we've got our hypotheses. Now let's have a go at actually doing this question. Now the first thing is, we're not given a p. Now we can work out this p, and because we'd have to work it out anyway, it changes our degrees of freedom. So we're not going to need the degrees of freedom till the very end of the question, but let's just work out the p anyway. So p, well, how do we work out p? Well, p will be my probabilities of success. So my success would be kind of like your discrete random variables. If you've got no oak trees here, you times it 1, we've got no oak trees. If there's 1 oak tree per square, we've got 4 of them, we've got 4. So we're going to have to sum all these multiplied together. So for example, I'll start rounding down and then I'll just give the answer. So it'd be 1 times 4 plus 2 times 21 plus 3 times 23 plus so on and so on. So that will be my numerator, and my denominator, now Liam thinks that there's 6 oak trees per square, and that it's 80 equal squares. So that, my denominator will just be 6 times 80, which will be 480. So my denominator is much easier, it's going to be 6 times 80. Okay, so P. This here, my numerator, this sums to 264, and my denominator is 480. And if you calculate this, you get 0.55. Okay, and because we've had to work out the probability for this question, sometimes you'll be given it, but for this one we wasn't. So my degrees of freedom we can work out after. But the formula for this will now be V equals N, well that's my number of columns for my expected frequencies, minus 2. Okay, so we'll need that for after on. We'll just write that down now. So now let's jump into working out the formula we need. So the formula you can use is my observed minus my expected all squared divided by my expected. Okay, and we need to do this for our values here for my expected and my observed. The first thing we always have to check though for the expected, do we have any expected values less than 5? Okay, so this one's just above. Looking across, then there's just this one. So your expected frequencies that are going to be below 5 are usually either at this end of your table, or they'll be at both ends. Now in this case, it's just this end here, it's just this one here that's problematic. So we have to pool these two together now. You always pool it with the adjacent column. So if you pool these together now, add these together, and what you get is 13.08. Okay, so if I just write that up here, just so you can see it a bit better, 13.08. So in essence now we've got 1, 2, 3, 4, 5 columns here. So we can actually work out the degrees of freedom straight away. So that'll be V equals 5 minus 2. Okay, so we've got 3 degrees of freedom. So we've got 3 degrees of freedom. I'll just put DOF. So we've got 3 degrees of freedom. Now we just need to work out this formula here, and then we need to sum it up to work out our chi-squared value. So to do this now, well, because this first one here is 0 or 1, you're going to have to add your frequencies here. So that would be 5 minus 5.53. So I'll just start doing the first one. So it'd be 5 minus 5.53. Square that. Then divide it by your expected, which was 5.53. So you've got to sum all of these up. Plus, and then you do it again. So it'd be 21 minus 14.89. 14.89. That's all squared. And then you divide that by 14.89 again. Okay, and you're going to have to keep doing that all the way up to the very last one. So that'll be your 5th column here. So we close that. So I'll write them down individually. So what I got if I do them up here. So my first one, so that'll be this one. That was 0.051. My next one was 2.51. Next one, 0.0654. Just go underneath for the next two. I also got 3.84, so you should get 5 in total. And then finally, 24.771. Okay, so them are my 5 values. There is another formula you can use. You can also use, if I just do it down here, you can also use the observed squared, so observed squared over the expected. You can use the sum of that minus your n. Both these methods will work. Okay, so whichever method you're more comfortable with. This one, okay, this formula is in your formula book. This one isn't. This one I think is a little bit easier sometimes, but this one is in your formula book, so you don't have to actually memorize it. It's just whichever you prefer working with. Okay, so these are my 5 values. So all I've got to do now is sum them, and I've got my value. Okay, so if you sum all these, your expected frequencies here. So I've accidentally copied one down wrong. I've accidentally copied this one down wrong. I'm going to say that's incorrect. This one here. So I'll just scribble that out. That one there should be 1.85. I'm going to say that one's much larger than the others. 1.85. Okay, 1.85. So we've got all them now. All we need to do is add them together. So if you add these together, so the sum of all these, well, that's going to be equal to 8.313. Okay, so 8.313. So now we've got the degrees of freedom. So this is my test statistic. So test statistic 8.313. My critical value, so now you need to use the formula book, so it's page 36. What significance level? 5% significance level, so make sure you read from 0.05, not 0.95, that's a common mistake. So 0.05, and we've got 3 degrees of freedom, so that'll just give you a critical value of 7.815, okay? So 7.815, so because our test statistic, I always struggle saying that word, is bigger than my critical value, we need to reject H0, okay? So reject H0, reject H0. So what did we say? So this distribution is not suitable. So reject H0, T distributed binomially is not suitable. And there we have it. So we've shown that this is not suitable. So we've got a bigger test statistic than my critical value, so we can reject H0. If that had been smaller, we would have accepted, and this would have been suitable. But in this case, it works out that it's not suitable. Okay, so again, you can use this formula down here. This will give you the exact same value for here. Okay, whichever method you've been shown more in class, or you've used more in your formula book, or anything like that, whichever you're more confident with, just stick with that. Okay. But that is part B complete, so that's 7 marks there. So now, let's have a look at part C. So part C, we have to find the value of S and T. So this person here believes that a Poisson distribution could be used to model the number of oak trees per square, and she calculates the expected frequencies given in this table here. Okay, so these are my expected frequencies again. We have to work out S here and then T here. So how would we do this? Well, let's just write it in the probability now, because this is a Poisson. Let's work out the probability of a Poisson distribution. So P. So my formula is e to the minus lambda times lambda to the x divided by x factorial. Okay. So that's my formula for working out the probability. Well, if we say the probability that x equals 2 is equal to this formula, and we just submit x equals 2 here, and then we do the same for x equals 4, for example, we can obtain a value, right? And we've got it in terms of x is equal to 2. We can't use this one here because it's 0 or 1. We don't know exactly what x would be, and we don't know what it would be here. It's 6 or more. So the best one to use are the ones that we have an exact value. It's 2 and it's 4. Using these, we can use x. We can put it both in terms of probability of x equals 2, probability of x equals 4, and then we can use this to obtain a value for lambda here. That would be our mean. And once we've got that, we can then work out probability that x equals 3, and probability that x equals 5. Now let's just be clear, when I work this out, these aren't the exact probabilities, because don't forget these here, these have been multiplied by 80 to give the expected. So if you divide these by 80, then that would actually give you your actual probability, okay? So that's why they're bigger than 1, because clearly you can't have a probability bigger than 1. So just to make that clear, because that's what will happen here now. When I work these out, they're going to be larger than 1. So just to be clear, obviously my probability isn't bigger than 1. But if we do that now, so the probability x equal to 2, that's going to be e to the minus lambda times lambda squared all over 2 factorial, which is 2. Okay, so that's that one nice and easy. X equals 4, again e to the minus lambda to the 4 all over 4 factorial, so 4 times 3 is 12, times it by 2, then times that by 1, I'm just going to get 24. Okay, so now we've got these two probabilities here. Now, I need to work out a value for these. Well, we know this is equal to 16.07. Okay, using the data we've got here, that's 16.07. This one's equal to 14.58. So we can use this now to work out our probabilities for 3 and 5 once we've got a value for lambda. So what I'm going to do now is I'm going to divide both of these. Okay, so it doesn't matter which way you divide. You can have to do 16.07 divided by this, or you can do this divided by this. Either way, it doesn't matter. As long as your workings are all, exactly fine, then you'll get the same lambda value as I will do it. So I'm going to divide it as 16.07 over 14.58. But like I said, this does not matter at all. Just be very careful when you're working. So my 16.07 is this, so it's eta minus lambda squared all over 2 times, so if you're dividing, I'm going to times it by 1 over this, so it's going to be 24 over eta minus lambda to the 4. Okay, so that's my working there. Now we just need to actually evaluate this. Well, 24 over 2, so that'll cancel with that, and that'll give me 12 there. My eta minus lambda will cancel with that one there. So all I'm going to get is 12 lambda squared over lambda to the 4. 12 lambda squared over lambda to the 4. Okay, and this is equal now. If you actually evaluate this, I'm going to write it out in full. So it's going to be 1.102194,787. Okay, 787. So that's equal to this. So now this, we can simplify this again here. That's going to be 12 over lambda squared. So therefore this is equal to 12 over lambda squared. So now I'm going to times this across by lambda squared. So if I do it up here, I'm going to get 1.102194,787. Lambda is equal to 12. So now you've just got to divide 12 by this, and then we need to square root it because this is lambda squared, so we're going to say we're missing some at lambda squared, and then square root your answer. Okay, so if you do that, what you'll obtain is that lambda is equal to 3.299601153. Okay, so obviously you could round that, but for now I'm just going to keep it as 4 degrees of accuracy, because we can use this now to obtain these two probabilities here. So for now, you can either use the formula again here, or you can just plug this bit in on your calculator now. So I'm just going to put this on my calculator just to save time. And I'd recommend, if you've got a graphical calculator, guys, always utilise it for these questions. And for your further stats exams in general, really important skill. So looking at the probability that x equals 3 now. Plugging this in on my calculator with this mean, and my x being equal to 3, what I'm going to obtain is that this probability is equal to 0.22. Again, I'm just going to write these out in full. 0.22091973. And my probability that x equals 5. That will be equal to 0.12026172. Okay, so we've got our two probabilities. Now we just need to times these by 8, right? So that'll give me my s. So therefore, s is equal to probability of x equals 3 times 80. So I'm not going to write all this out again. I'm just going to do the calculation and then round it to 2 decimal places. So that'll give me 17.67, and then t, same again, it'll be a probability but with x equals 5. Times that by 80, and that's my value, just round it to 2 decimal places. And if you do that, you'll get 9.62. Okay, so there we go, we've got the answers, or the values for s and t, with both to 2 decimal places. So let's clear all that. So now we're on to part D. So this question just feels like it's going on forever. It's quite a long one. I might leave the timestamps in the description just so you can skip through if there's a certain part you want to get to. So let's carry on. So part D. So a similar question here. We have to write down the hypotheses to test the suitability of this model. So just like we did with part B here, I've got my two hypotheses. So H0. Well, we're testing whether the Poisson distribution is a good model or a good fit for the distribution. So if I just write that, Poisson, remember H0, that is a good fit. So Poisson is a good fit, or a good fit for the distribution. And then H1, Poisson is not a good fit. Okay, so there we have it. So H0, that is a good fit. H1, it's not a good fit. So that's part D done. Nice and easy, just 1 mark. Part E now, we're given another test statistic, 8.749. We just have to complete the test, okay? So let's look at our expected values first. So part E, well, we have S, that was, just give me a second, I've moved them out of the way. So my S was 17.67, so we'll just write that over there, S equals 17.67, and then my T, that was equal to 9.62. So S and T, that's these. Well, all these values are greater than 5, right? So we don't need to do any pooling. So that's the first thing. So no pooling needed. So the good thing is that we don't need to do any pooling. So now, let's work out my degrees of freedom. So my degrees of freedom, how many columns have we got? 1, 2, 3, 4, 5, 6. It's going to be 6. And again, we're going to subtract 2. Because we've got for the totals, and we've got it because we estimated lambda, okay? So that'll be 4 for my degrees of freedom. Again, we're going to use page 36, right? So we're going to use page 36. Because I just need a critical value now, you know, to compare this test statistic to. So critical value, again, page 36. This will give you 9.49. And again, it's a 5% significance level, so it's 0.05, and then go across from 4. So you get this 9.49. So this time, my test statistic is smaller because it's 8.749. So because it's smaller, we have to accept here. So therefore, accept H0. So that means the Poisson is a good fit. So Poisson is a good fit. For Simon's model. So there we go. So that's part E done. So nice and easy. Just got to work out the degrees of freedom, work out your critical value, and then just accept based on the fact that it's smaller. And then finally for part F, it says, using these results of the test, explain whether the origin of this woodland is likely to be cultivated or wild. Okay, so we've got to use all the previous information we've just worked out from part A, B, C, D, and E to give us the answers for F. So what it means, or what it's asking, is that are these trees basically planted randomly, so they're wild, or are they planted in a more specific manner, you know, maybe to a pattern, so it'd be cultivated? Well, what we just worked out is that Poisson is a good fit. Poisson, good fit. Now, if Poisson's a good fit for this model and this distribution, what that would suggest is that they are planted more randomly, because binomial, in theory, gives us a more proportionate amount. It's going to be planted almost methodically. But with it being Poisson, what that implies is that it's almost planted randomly. Okay, so planted randomly. So planted randomly. So if they're planted randomly, that would suggest that the origin of the woodland is likely to be wild rather than cultivated. And there we have it. So that's question 4, finally fully complete. Moving on to question 5 now, we have a question here on hypothesis testing, as more specifically hypothesis testing with the Poisson distribution. Okay, so what we're told here is we're looking at information that's collected about accidents on a bypass, and it's found that the number of accidents per month is modelled with a Poisson distribution with mean 2.5. For the next part, it just tells us that this is changed to a series of 3-month periods that are recorded, and then it wants to test whether or not there was a change in the mean number of accidents per month. So for part A, it's just asking for us to state our hypotheses clearly and use a 5% level of significance to find the critical region for this test. So we've got to state the probability in each tail as well. So first off, let's write in the hypotheses here. So H0, well, this is for a 1-month period here, this 2.5. So if we want it for a 3-month period, all we've got to do is scale that up. So we're going to have to times it by 3. So 2.5 times by 3, well, that's going to be 7.5, right? Our lambda is going to be equal to 7.5. So let me just undo that, 'cause I need to put my lambda in. So let me just undo this, this is really bad. So it's going to be h naught lambda, so the mean, that's going to be equal to 7.5. Okay, my h1, so we've got to decide whether it's a one-tailed or two-tailed test. Well, because we're only deciding whether it's changed, it's not increased or decreased, it's going to be a two-tailed, right? So we're not specifically looking whether it's increased or decreased, so it's two-tailed. So that's lambda is not equal to 7.5. So two-tailed test. So I'm just writing this over here, this isn't part of my hypothesis here. So two-tailed test, so that means, because it's 5%, that's 2.5% at each tail. Each tail, okay? So, what we're going to have to do first is we're going to have to consider the upper boundary's lower region, and then we need to consider the lower boundary and the upper region for that. So, for this question, you need page 35 in the new Edexcel formula booklet for Further Maths. So, Further Maths formula booklet. Okay, so for the upper boundary lower region, so I'm going to call this UB upper boundary lower region. Well, what we're looking for here is the probability that x, so let me just write down my model first. So my model is that x is distributed with a Poisson with a mean of 7.5. So I'm looking for the probability that x is less than or equal to C1. Okay, that's just going to be my variable here, where this is close as possible to 2.5%. Close as possible. Close as possible to 2.5%. So how do I work out this C1 value? Well, all you've got to do is use the tables in the formula books. If you go to page 35, make sure you're looking across at lambda equals 7.5, because that's our model. And then you're going to go down and you want it to be as close to 2.5%. Well, the closest one there is when the probability for x is less than or equal to 2, okay? Because the value here for 2 is 0.0203. So therefore, my lower critical region, is x less than or equal to 2. Okay, so that's lower, believe it or not, lower critical region, and x must be less than or equal to 2. Now we can do the same with the the lower boundary upper region. This is a tongue twister between the two of them. So if I call it LBUR, what I need now is kind of the opposite. So I need the probability that x is greater than or equal to C2. And this again has to be as close as possible to 2.5%. Close as possible. To 2.5%. Now, because this is x being greater than or equal to C2, what I'm going to have to consider is using the tables again. So again, page 35, and make sure you're going across with lambda equals 7.5. I need the region which is going to be closest to 2.5% again. Now remember, because this is greater than or equal, well, what you find is the closest value here is when it's 13, right? But because this is greater than, so if I just do it over here, remember when you calculate a probability, say x less than or equal to C2, this is going to be 1 minus the probability of x. So if I just put a number in there, sorry. So I say that's 5, that'll be 1 minus the probability of x being less than or equal to 4, right? So, doing the same now, I get my value here of being 0.0216, okay? Now this is when it's 13. So my actual probability for this must be x being greater than or equal to 14, right? Because it's going to be 1 minus this. So therefore, this is going to be 1 minus this, or 1 minus probability of x being less than or equal to 13. So therefore, it must be 14 for my critical region. So if I just write this down over here, sorry, so upper critical region. So I'm kind of running out of room here. Hopefully, I should just fit it on. upper critical region is when x is greater than or equal to 14. And the probability for that is, like we said here, 0.0216. Okay, so them are the probabilities in each tail, and we found the critical regions for these tests. So that's all of part A. We don't need to do anything else. So let's just clear all that. For part B, just on 1 mark, we have to state the probability of a type 1 error using this test. So, type 1 error. Well, a type 1 error is when you reject when you shouldn't have. So, type 1 error is a reject when you shouldn't have. Okay, so the probability of doing that, well, that's just going to be simply my two critical regions from the last, my two critical probabilities, right, from the region. So if I add them two together, I'm going to get my probability of a type 1 error. So that's going to be, if I add them together, 0.0203 plus 0.0216. Add these together now, what do we get? Well, you're just going to get 0.0419. And there we go. So that's just a probability of a type 1 error using this test. Okay. Part C here. Well, what it's saying now is that the data from the series of 3-month periods are recorded for 2 years. And we have to find the probability that at least 2 of these 3-month periods give a significant result. So, how do we do this? Well, this is similar to the question 2 we did for this paper with the Poisson distribution again, where we're taking it in terms of a period now. Here, so we've got a 3-month period, this is recorded for 2 years, but it wants to know how many of these 3-month periods give a significant result. So we're not actually going to use the Poisson here. Hopefully you can spot that we're going to need the binomial now, okay, because we're modelling it in a number of different periods, right? So this is going to be y is distributed binomially. My sample here, well, how many 3-month periods go into 2 years? Well, that'll just be 8, because there's going to be 4 lots of 3-month periods in 1 year. That'll be 8. Now we want a significant result, sorry. So that'll be using the probability here, because this is where we get a significant result. So it's going to be 0.0419. So using this now, we need to work out the probability that at least 2 of these 3-month periods give a significant result. Well, that'll just simply be the probability that y, because we're using the model y, is greater than or equal to 2. This is my model for at least 2. Well, that's going to be 1 minus the probability that y is less than or equal to 1. And if you just plug this in on your calculator now, using the binomial distribution on the stats mode, you're going to get 0.0415. And there we have it. So that's the probability for C there. And then finally for D, we have to find the probability of a type 2 error. And it's modelled by a slightly different scenario, because after the work's completed, the actual mean is 2.1 per month. Okay, so I'm going to need a new distribution now. So if I clear this, so if it's 2.1 per month, and we're looking at a 3-month period, well, I'm going to have to scale that up by 3, right? I'm going to have to times it by 3. So my new distribution is y is distributed binomially with a mean of 6.3, okay? Because 2.1 times 3 is 6.3. Now, we need to use the critical regions that we already worked out in part A, because we're using the test in part A. Well, we worked out the probabilities here. Well, when y is less than or equal to 2, and that would also be when probability of y is greater than or equal to 14. Okay. Well, using this information now, oh, sorry, this is a Poisson, sorry, I don't know why I put B, that's a Poisson there. So now I've got my two probabilities here. Just using my calculator here, my Poisson distribution on my stats mode to get my two different probabilities here. So it's going to be 0.04984649317. Now I'm going to write all my digits down. Obviously you don't have to show these down individually on paper if you can just times them, but I'm going to show it just so I don't lose any degrees of accuracy here. This one will be 1 minus the probability of x being less than or equal to 13. So that's going to be 0.005485286. I'm just making sure I don't accidentally write this down incorrectly. Now, like we did in part B, we need to add these together, but because it's a type 2 error, we then do 1 minus the sum of these. So therefore, type 2 error, well, that's going to be equal to 1 minus the sum of these. So what's the sum of these? That's going to be 1 minus the sum of these together, which will give me 0.05533178177. And then if you calculate that, you're just going to get 0.945. So 3 significant figures. And there we have it. So that's question 5 fully complete. Moving on to question 6 here now, we have a question on a probability generating function for a discrete random variable x. And the function we've got is k ln bracket 2 over 2 minus t. So pretty standard here, we just got to find the exact value of k for the first mark. Then part B asks us to find the exact value of the variance. And then part C just asks us to find a probability. So let's jump straight into this. It's pretty nice as a question here. So for the exact value of k, well, you've just got to be aware of the fact that if you sub 1 in here for t into this generating function, this whole function will be equal to 1. So what we're saying here is that g of 1 makes the whole function equal to 1. So can we use this now? Of course we can. We can use this now to obtain the value for k. So what we're saying is that k ln, now where there's a t, we put 1 in, so that'd be 2 over 2 minus 1, so that'd be, this is the same now as ln of 2 minus ln 2 minus t. But if you put t in there, this becomes ln of 1, which is equal to 0. So all we get left with is ln of 2. So this becomes k ln 2 is equal to 1. Okay, so k ln 2 is equal to 1. Now to get k, just got to divide through by ln 2. So therefore k is equal to 1 over ln 2. Okay, and there we have it. So that's the value for k just for the first mark. Okay, so part B, 7 marks. There's quite a lot, so I'm going to clear this so we've got hopefully enough room. So for part B, we've got to find the exact value of the var of x, or the variance. Okay, so how do we do this? Well, the formula for the variance here is given as this. So you've got to work out derivatives for this. So it'll be g prime prime. Oh, sorry, let me just ignore that. So this will be when you sub in 1, right? So we always sub in 1 for the variance of x plus the first derivative at 1 as well. So g prime of 1, and then we minus this off a squared. So it's minus g prime of 1 all squared. Okay, that's the formula we need. So for us to be able to do this, we're going to have to differentiate this. So if I write the function over here and I'll write the derivatives. So g, if I just write it as g, well, that's going to be equal to k lots of ln 2 minus ln 2 minus t. Okay, so I'm splitting these ln's up here. And I know we have what the value of k is. We have the exact value, where k is 1 over ln 2. But for now, I'm just going to keep it in terms of k, and then at the end, I'll sub my k value. Okay, so you can do it here at the beginning, but I think it just makes it easier to do it at the very end. So, doing this now, differentiating this. So g prime, if I call it g prime of t just for now, well, how do we get this? So we're going to have to differentiate this function here. Well, ln 2, that'll just differentiate as 0, minus ln bracket 2 minus t. So 2 minus t, the derivative of that will be minus 1 times the minus on the outside. So what I'm going to get here is, it'll be k lots, because we need the k still, of 1 over 2 minus t. 1 over 2 minus t. Okay, and we can rewrite this, and it'll make it easier because we've got to differentiate this again. This is the same as k over 2 minus t. And again, just one little step further, this will be k lots of 2 minus t to the power of minus 1. Okay, so we've got to differentiate this again. Hopefully this is relatively straightforward. So g prime prime of t. What will that be? Okay, so just differentiate this here now. So differentiating this using chain rule, you're going to get k lots of 2 minus t to the minus 2. Okay, so that's the second derivative. So we've got the second derivative, we've got the first derivative, we've got everything we need now for this. Now all we've got to do is plug in t equals 1. So, therefore, variance of x Well, that'll be equal to k lots of 2 minus 1 to the minus... so what we're doing first, we're doing the second derivative first. So that was this one here. So it's going to be k lots of 2 minus 1. So 2 minus 1 to the minus 2 plus this g prime of x. Well, my g prime of x is this, so plus k lots of 2 minus 1 again to the minus 1. And then finally, we're going to minus this off. So it's going to be minus k lots 2 minus 1 to the minus 1 all squared. Okay. Well, 2 minus 1 to the minus 2, that's just going to be 1. So I'm going to get k. Same again here, 2 minus 1 to the power of minus 1, that'll just be 1. I'm going to get another plus k there. And if this is plus k, this is the same thing, just squared, and I'm minusing it, so it's going to be minus k squared. But we know, up here now, that k is equal to 1 over ln 2. So just plugging in my k now, it's going to be equal to 1 over ln 2 plus 1 over ln 2. Finally, minus 1 over ln 2 squared. Like so. And there we have it. So that's part B fully complete for the 7 marks. And now finally, we've just got to find the probability that x equals to 3. Well, for this here now, the probability that x equals to 3, well, we've just worked up to the second derivative. So we're going to need the third derivative. So I'll just write down the second derivative again. Well, that was equal to k lots 2 minus t to the minus 2. Okay. But we need g prime 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 of t. And once we've got this third derivative, we can use the coefficient of t cubed using the Maclaurin series. And remember the Maclaurin series is about the point 0, okay? About 0. So if it's about 0, that means we're going to have to sub in t equals 0 for our final probability, okay? So we need now g prime prime of 0, okay? So doing all this now, the derivative will be, if I do it over here just so I've got enough room, it's going to be k lots of 2 over t minus 2 minus t, so let me just undo that, sorry, 2 minus t, 2 over bracket 2 minus t all cubed, and then writing that in terms of k, well k is 1 over ln 2, so 1 over ln 2 times 2 over 2 minus t cubed when t is 0. Well, what would I get when t is 0? So that's going to be 2 over 2 cubed, so it's going to be 2 over 8 or 1 over 4. So I'm going to get 1 ln 2 times 1 over 4. So I'm going to get 1 over 4 ln 2. Okay, so 1 over 4 ln 2. So all I've got to do now is plug this in using the Maclaurin series. And remember, the coefficient of t cubed for this case would be the third derivative, so g prime 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 at 0. The denominator here will be 3 factorial because it's the third term, okay? So 3 factorial, well what's this going to be? Well we know this already, that's 1 over 4 ln 2. 1 over 4 ln 2. And this is divided by 3 factorial, so that's 3 times 2 times 1, which is equal to 6. And if you've got 1 over 4 ln 2 divided by 6, that'll simplify to 1 over 24 ln 2. And then just put this into your calculator and get a value. So if I did this to 3 significant figures, you get 0.0601 to 3 significant figures. And there we have it, that's question 6, fully complete. And finally, moving on to question 7 here, we have a question on the geometric distribution. So for this question here, for part A, we're just asked to find 2 probabilities. So what we've got here in this question is a spinner, which can land on either red or it can land on blue. So when it's spun, the probability is a third of it landing on blue. So what that means straight away is we can write down the probability of red will be 2/3. So the probability of R is 2 over 3. If the probability of blue is 1 over 3. Okay. So part A just asks us to find the probability that the random variable B, so that's the number of spins when the spinner first lands on blue, so that's how we know it's geometric, because it's going to be a number of failures before it is a success. So it's how many times does it have to, what's the probability where it lands on blue on the 4th attempt. So if we write this down, the probability that B is equal to 4. Well, for this one here now, remember, what it's doing is it's landing on the 4th attempt, so what that means is it's a failure, followed by a failure, followed by a failure, followed by a success. Okay, that's when it lands on blue. Well, I've wrote them as F and S, but my failure would be my red. We don't want red, that's a failure, and my success would be blue. That's when it lands on the one we want. So that's failure, followed by failure, followed by failure. So that's 2 over 3 times 2 over 3 times 2 over 3. Well, we can just simply write that in index notation. That'll be 2 over 3 to the power of 3. And then the success is 1 over 3. So it's 2 over 3 cubed times 1 over 3. Well, 2 cubed times 1, so that'll be 2 cubed. And then finally, 3 cubed times 3, so that's 3 to the power of 4. And then if we work this out, 2 cubed is 8, and then 3 to the 4 will be 81. And there we have it, 8 over 81. So that's the first part. And then for the next one, so II, we have to find the probability that B is less than or equal to 5. Okay, so again, this one's pretty straightforward. Just got to be aware of the fact that when it's less than or equal to, we do 1 minus, okay, 1 minus the probability that B is greater than 5. So, probably that B is greater than 5, well, that's just going to be 1 minus, okay, the probability that it's red, so that would be 2 over 3, so 2 over 3, and then we raise it to the power of how many times, so because it's 5 here, we raise it to the power of 5. Just plug this in on your calculator, you don't have to sit and work this out, it's not about the actual calculations, but you'll get 211 over 243. Okay, so that's the first two parts for A, fully complete. So let's have a look at part B now. We have to find the expectation of B squared. So part B, E of B squared. Okay, so the formula for the variance is as follows. So that the variance of B, which you should be very aware of now if you've studied further stats 1, so it's E of B squared minus the expectation of B all squared. So minus, put it in a bracket, B all squared. So that's how we work out the variance. Well, the expectation for B here is really easy. To work that out, all we do is we do 1, so it's 1 divided by the probability. Well, in this case, the probability of blue is 1 over 3. So it's going to be 1 divided by 1 over 3, which is just simply 3. Okay, so that's the expectation of B. Now, we need to work out the variance. So, variance, we'll just call it sigma squared. That will be 1 minus P all over P squared, where P is your probability again for blue. So this should be the sigma squared of B. Well, P is a third, so 1 minus a third divided by a third squared. 1 minus a third, that's 2 over 3. A third squared would be 1 over 9. So this would give you 18 over 3, which would just simplify to 6. Okay, so we've got these little bits of information now. Now we can work out the expectation of B squared by just rearranging this. So we know E of B squared, well, that's equal to the variance of B plus this, right? We take this onto the other side, balance the equation, we're going to get it. So that's the variance of B plus the expectation of B all squared. Well, we know the variance of B, that's 6. The expectation of B is 3, so if we square that, plus 3 squared, so that's equal to 6 plus 9, which is just going to simply be 15. Okay, so that's how you find the expectation of B squared. So we've got through the first two parts. Finally, let's move on to part C. So we're given a bit of information to start the question. So they're playing the game with this spinner, so she must choose a colour, either red or blue. Steve will spin it repeatedly until the spinner first lands on the colour that Tamara has chosen, and the random variable x represents the number of the spin when this occurs. So if she chooses red, her score is e to the x, and if she chooses blue, her score is x squared. But notice this x squared here can be this e to the b squared here, okay? So we can use that, part B, to help us, but we're going to have to work out this e to the x part here for red. So how do we do that? Well, let's model it with another geometric distribution. So let's let R be the number of spins when it first lands on red. So write that down. Let R be number of spins when it first lands on red. When first lands okay. So I'm going to model this now using R distributed geometrically with my probability being 2 over 3, okay, because that's the probability that it lands on red. So using this now, we need to work out the expectation of e to the x. So how do we do that? Well, that's just going to be the sum from x is equal to 1 to infinity of e to the x times, now this is by 1 over 3, so just like we would for the normal probabilities here, 1 over 3 x minus 1, and then you times it by the probability of success, so that'd be 2 over 3. So just like we did in part A here, where we did probability B being equal to 4 and so on, doing the same notation here, but we're putting it exact, we're using e to the x. So now, we've got to evaluate this summation. So this looks tricky on paper, but if you're ever unsure how to calculate a summation, just write down a few terms and see if you can spot the pattern, what's going on. So let's just let x be equal to 1. So when x is 1, what do we get? Well, I'm going to get e to the 1, so that's just e times 1 over 3 to the 1 minus 1, so that's just going to be a third to 0, so that's 1 times 2 over 3. So what I'm going to get is 2e over 3. Okay, so I get 2e over 3. Let's let x be equal to 2. So when x is equal to 2, what do I get? Well, I'm going to get e squared times 1 over 3 to the 2 minus 1, so that's a third. So at the minute I've got 2e squared over 3 and then times that by 2 over 3. So plugging that all together, I'm going to get 2e squared over 9. And then finally, let x be equal to 3. So you might have already spotted the pattern, but if I do one more, hopefully it'll make it extremely clear what the pattern is. So that's going to be e cubed times a third x minus 1, so that'll be a third squared. So we've got e cubed over 9 at the minute, and then we times that by 2 over 3. So I'm going to get 2e cubed all over 27. Okay, so can you spot the pattern here? Get me to each term. Well, all I've got to do is times this by e over 3, right? If I times that by e over 3, I get 2e squared over 9. Times this by e over 3, I get this. So what I've actually got here is my geometric series, obviously, but it's going to be an infinite geometric series, right? I can work this out and I can actually evaluate it. So if I just do it over here to evaluate it, you sum to infinity, that's equal to a over 1 minus r, where a is your first term and r is your common ratio. So my first term is my, when x is 1, so that's 2e over 3. So 2e over 3 divided by 1 minus r. So 1 minus my common ratio, so 1 minus e over 3. Now, all you've got to do is actually evaluate this, okay? So if you evaluate this, what do you get? Well, you'll get 19.29a, so on and so on, okay? So that is now my expectation for e to the x. And we know the expectation for x squared, that is what we just worked out in part B. So what was that? I can't remember what I wrote down. That was 15. There we go. So we want the one that gives us a larger number on average. So that will be e, the expectation of e to the x. So therefore, Tamara should choose red. So therefore, Tamara should choose red, because it's got a higher expectation. And there we have it. So that's the end of this Further Stats 1 paper. Be sure to subscribe if you're new around here. I'm going to be going through all the new A-Level Further Maths papers and revision content.